Okay, I started the recording. Ryan, do you want to present the do you want to do the tensor part of it? Yeah. That's like part of it. All right, so I'm gonna wait 3 more minutes before we get started. Start 5. So before we get started, everyone should open up Google Colab. So the way it's gonna work is we're gonna present some topics and then we're gonna run through actually applying those topics using PyTorch and Python. And you can run PyTorch code online super easily on a place called Google Colab. And at the end, we're gonna have QR codes up so you can look at the finished versions. On the side for reference.
Wait, can you like link it?
It's linked in here, but
Okay, it was like the one I messaged you on.
yeah,
Yeah, it's like the same thing.
it's right here.
Okay, yeah.
I'll open it up here so you can.
Wait, actually, I think you should explain this one first. Shit. Yeah.
Yes. You want to explain this line?
Nah.
Okay, then just run through the example.
Yeah.
That's good. Oh, I'm very intimidated. All right, looks like people have finished coming in, so we're gonna get started now. So like I said, for people that just came in, open up a Google Colab, and at different parts of the presentation, we're gonna do some live coding, and you guys can follow along. So this workshop is about neural networks, just a brief introduction, what they do, where you can use them, and how to use them. So before we get started, we need to learn what a tensor is. So who here has taken linear algebra? Who here has taken Calc 3? All right, so that's a really good portion of people. So a tensor is kind of just like a generalization of a matrix. So if you say have a bunch of matrix stacked together, and instead of just a grid of values, it's like imagine a cube of values, you'd call that a tensor. And they're neat for a bunch of reasons. One like easy example is representing images, right? Say I have an image that's like 128 by 128 pixels, but with a matrix, I can only represent, say, a black and white or a grayscale image. But if I want to represent an RGB image, then each of those cells essentially needs to have 3 values. And I could also just make that 3 separate matrices for red, green, and blue. So that's just like a quick example of where you'd use a tensor and why we even have them in the first place. So stuff you can do with tensors. You can add, subtract, you can multiply element-wise, you can dot product, the same as matrices, and you can reshape them. So adding, subtracting, and element-wise multiplication, you can only do that if 2 tensors are of the same size. If you don't, and you try to, in something like PyTorch, it's going to say you have a dimension mismatch, and that's probably why. So the reason you would, in any case where you need to do operations of two tensors with different sizes, there are methods you can use to kind of get them to be the same size. So you can say repeat a matrix across one dimension, and that would turn into a tensor. You can add zeros in a bunch of places to make it a certain size. And we're going to get to some of those tricks later. But for now, let's just do some basic like tensor operations and see what it does. So Brian, do you want to open the finished version?
That is the finished
Yeah, the finished version. But do you want to like run through it or?
Oh, I was gonna like try like show that on the.
Oh, yeah.
Okay. Wait, it looks really weird.
I can make it bigger or small.
Yeah.
Okay,
Okay.
everyone read that? People in the back as well? Yeah.
Okay.
Yeah.
Thank you.
Is that good for everyone? All right. So, yeah.
Okay. So first you want to like import PyTorch. So this is like this one-liner. Shit, like I'll just do that. And then like you said, tensors can be thought of as like n-dimensional arrays. So for example, like a vector like this, like 1, 2, 3, that can be thought of as like a one-dimensional tensor. A matrix is like a two-dimensional tensor. You can get like three-dimensional, four-dimensional, five-dimensional tensors, and so on. And so if you want to create a tensor, you just do torch.tensor, then you just like put in this array. So this is, if you're familiar with like NumPy, it's like sort of something similar where like in NumPy you have like a equals np np dot array like 1, 2, 3, and so on. So this is like really similar, and you can actually, I didn't include this here, but you can convert a NumPy array into a tensor array. I mean a PyTorch tensor, and then vice versa. And so I'll just like run this. So you can see like the first one is like a one-dimensional tensor, second one is a two-dimensional tensor, third one is a three-dimensional tensor, and so on. These are like some operations. So you can do addition and subtraction with tensors. So for example, if I just run this one, you can see, 579, that is this tensor plus this tensor. This one is like the difference of those. And then you can also add a scalar. So this will add like element wise to your tensor. And then like he also mentioned before, like if there's a dimension mismatch, you'll also get like an error. So for example, or say, yeah, so it says size of tensor A, which is 2, because tensor A has, wait, the hell?
I think it's from the
Oh,
previous
sorry, yeah,
one.
it's from the previous cell. So yeah, this one is 2 dimensions, this one is 3 dimensions, and so you can't add those two. So that's why you get an error. And this is like some multiplication. Maybe that's it. Just so you can see a little better. You can multiply like a tensor with like a scalar. You can multiply it element wise. And you can also do matrix multiplication with like 2 tensors. So the sort of like function you have to call is torch.matmul, or you can just use like this at symbol, and you can see like you get the same results. And then this is like some tensor manipulation. You can transpose a tensor with just .t here. So you can see this is like the original tensor. This is the transpose tensor, which just means just like switching the columns and the rows. And then you can reshape a tensor. So originally tensor A is, wait, the hell? It's this is a 2 by 3 matrix, and then you can reshape this to a 3 by 2 matrix, can reshape it into a 6 by 1 matrix, and so on. And you can also use this -1, and this -1, it basically just PyTorch just basically infers what dimension will be put into that. So can any of you guess what this is equivalent to if I just put -1?
Well, yeah, it's right there. But...
Oh shit, wait. No, you don't see it. Does anybody know? Oh, did I hear 3? Yeah, that's right. Yeah. So yeah, you can do that. And the reason why you can't do this So trying to reshape into a 3x1 matrix is because there's 6 elements. And so, 3 times 1 is 3, which is not equal to those 6 elements. So yeah. Oh,
Oh, yeah.
sorry, what?
Excuse me. Can we find this online?
We're
Yeah, I
gonna
think
have
we'll-
QR codes and we're also gonna post links at the end of the presentation.
Okay.
Yep. Does the mic work? No. Is that better? Yeah,
Oh,
all right.
Yeah, and then this is like some other random stuff. So you can get like
Yep, question?
this. Oh,
Oh, sorry, yeah, it is recorded.
okay. Yeah. So you can get like the sum of a tensor. You can get the max of a tensor. And this is like kind of important. So the device a tensor is on. So right now, if I just like run tensor A equals torch.tensor or whatever, it'll automatically be on the CPU. But then you can actually like get that tensor and move it to the GPU, which is really important when you want to actually do stuff on the GPU. So most of you probably know that you want to train your neural networks on a GPU because it's much faster. So you have to like put all these tensors on the GPU so that it actually does the operations on that device. And so if you do like, for example, okay,
But it's not gonna work on here because we
yeah,
didn't enable.
I don't, yeah, I don't have right now, but like if tensor A was on the CPU and then tensor B was on the GPU and you try to like add them or something, then you would just break everything. So yeah, don't do that.
If you do want a GPU, we're not really gonna be messing with that during this workshop because the model that we're training is fairly lightweight and it trains fast enough on the CPU itself. But if you do need to work with that, this is like the main function you'd be using. This is just saying, take tensor A, put it on the GPU, and after that, if you're doing any operations with it, the rest of the tensors that you're messing with also need to be on the GPU. Is that, can you hear me through the mic? I can't tell. Okay, I don't know how to use this. Is that better? I don't know. All right, cool. So, oh, another function that we want to go over in here, it's pretty convenient. So a lot of times when you're making neural networks and working in PyTorch in general, you're kind of going to get like a size mismatch and you're not going to have any idea why that's happening. An easy way to kind of debug that is you can print the size of any tensor. So let's take tensor 3 dot here. If you do dot size, it will print out the size of it. So here we can see it says it's 2 by 2 by 2. And we can just cross reference that with this. We can see on the outermost dimensions, we have 2 like subarrays. And in the next dimension, we have another 2 subarrays. And in the last dimension, we have, again, 2 elements. So if we instead did something like this, right, we put third value in the last dimension, we're going to get a different output here. The last number is going to be a 3 instead of a 2. So that's kind of just like a brief intuition of what tensor sizes kind of look like. So now that that's covered, let's move into the most basic building block of a neural network. This is called a perceptron. So before we even talk about neural networks or anything like that, we need to cover what a perceptron is. It is really simple. It's kind of modeled after a single neuron and like a human brain, but not really. That's kind of like the analogy of it. But what a perceptron does is you have a bunch of input values, x1 through x sub n, and you multiply each of those by a weight value. So you have weight 1 through weight sub n that corresponds to a single input value. And then you sum all of those up and you get a value. We call it z in this case. And then you send it through an activation function and we get a. So we're going to talk about why activation functions are more important later. But for now, just know that this just has to be some function that isn't linear, right? The most commonly used one is called ReLU. So I'll open up Desmos and show what ReLU looks like. This is the most commonly used activation function. And all it does is about if a value is less than 0, it makes it 0. If a value is greater than 0, it makes it that value itself. It just doesn't affect the value at all. So we're going to take a look at why having an activation function that's nonlinear is so important later. But for now, just know that that's a thing that exists. So now that we have a perceptron down, we can make a whole layer of perceptrons. So let's talk about just this hidden layer over here, and see how we can represent that as like matrix operation. So here we can see like the mathematical sort of definition for a perceptron is you have a weight at a certain index, you have the input value at a certain index, you multiply them together, sum them, and then send them through the activation function. But we don't want to be dealing with individual values. It kind of gets cumbersome when we get into big neural networks. So instead, we're going to represent them as vectors and matrices. So here, instead of having x1, x2, x3, whatnot, we just say there's one vector, x, and that contains all these values. And then same for the hidden layer. We're going to get into what that actually means later. We're going to represent all the output values of this layer as a vector called h. And then same for the final output. We're going to represent those values as a vector called y. And all of these three vectors are going to be of different sizes. Like, so the size of x is not necessarily the size of h. Like this can be like a 10-dimensional vector. This can be like a 15-dimensional vector. It doesn't really matter that they're same or different. So now, what happens when we put a bunch of perceptrons together is each of these cells, say in the hidden layer, we treat each of them as one perceptron. So if we had x1, x2, x3 over here, then the value of h1 would be equal to x1 times w1 and x2 times w2, all added together. And we do the same for the second h cell. And this one has a different set of weights, right? So h1 and h2, they don't share the same set of weights. So if we continue using individual numbers as we did in the previous slide, then we get this equation. So h sub j, which is like one element, one of these perceptrons, the value at that element is equal to the summation of weight sub I and j. So the weight value is not only unique to the input value, it's also unique to the hidden value, multiplied by the input value, added up together, passed through the activation function. And if you've taken linear, you might recognize that this is essentially the same as doing a matrix multiplication. So if we're using matrices, then we can just represent all of the weight values for this entire layer in one matrix, call it uppercase W sub h, and we do a matrix multiplication, like a dot product, by the input vector, we call it x, and again pass it through activation function, and we get the h vector. So actually, if I'm going to make it a tiny bit more clear over here. Did not mean to do that. So the vector x looks something like x1, x2, and so on. And the vector h looks something like h1, h2, and so on, right? So now that we know what a neural network looks like, let's actually try making one in PyTorch. Also, before we do that, the data set that we're going to be working with today is called MNIST. You might have seen this before. It's a fairly popular data set. All it is it's a bunch of images of handwritten numbers. So there are images of zeros over here on the first row and so on, right? And these images are 28 by 28 grayscale images. They're really simple to work with. And what we want to do is we want to train a neural network, which takes these images as input and gives us the actual number that's contained in those images. And this could be useful, like the real world application for this could be something like optical character recognition. Say you generalize this to not only numbers, but also letters, right? You could take a postcard and read the handwritten address off of it. So let's try making an actual neural network. I'm going to create a new notebook over here, and we import torch just as before. And we can also import, we also need to import a few other things. So there's for torch show NN. So this contains a bunch of like useful functions for representing parts of a neural network. We're also going to get torch.functional or torch.nn. And this contains, say, this activation function that we used earlier here. And that's all we need to import for now. And we can actually make a neural network. Oh, also, another thing I forgot to mention. When you have multiple of these layers, you just do the same thing for y as we did for h. So y would be equal to uppercase W sub y dot product the h vector, and then cover that with the activation function, and we get the vector y on the left side of that equation. So when you put a bunch of perceptrons together, you call that a multi-layer perceptron. So the way you define a neural network in PyTorch is you need to create a class, and it needs to inherit from the nn.module, like superclass. And if you haven't written Python before, this is how you define a constructor in Python. Yep. Oh, sorry. Yeah. Is that better? And this is kind of just boilerplate. Python is first. I'm pretty sure there's like a better way to do this, but this is what I have written down. So let's make a really simple neural network. And as we talked about before, we have an input size of 28 times 28. So let's just define those values. We need to decide what the size of the hidden layer is, and that's kind of arbitrary. I'm going to choose 512. If you find that a model is overfitting, like it's performing really well on a test data set, on a training data set, but not really well on real world data, then you can try reducing this. If the model isn't performing well, you can try increasing this. It's just something that makes the model more or less complicated. And we have 10 different numbers. So we need a output perceptron that represents each one of the possible answers that the model could give. So our output size is going to be 10. And now we need to actually define the matrices. We need to define a matrix for this middle layer, and we need to define a matrix for the output layer. We can do that using nn.linear. So what this is saying is, all I'm saying here is I want a matrix that that transforms input size into output size. So one dimension of it needs to be input size, the other needs to be output size, or sorry, hidden size. And then I'll also have the output layer. So self.output can be equal to another linear, and this will be hidden size to output size. Is everyone able to follow along so far? Cool. So this is just defining the matrices. Now we need to actually do the operations, like do the matrix multiplication, and that's fairly straightforward. So PyTorch convention is you define a function called forward. So here we get x. X is the same as the x in this case. And we say h equals f dot relu. Relu is equal to this function. So h is equal to f dot relu of self dot hidden of x. So this line over here corresponds directly to this equation over here. Like these two are equivalent. And then we also do y. So y equals self dot output of h. So it's customary to like not have an activation function for the output layer because the objective function, which we're going to get into later in terms of actually training, it requires that we don't have an activation function on the output layer. And finally, we return y as the output. So we can try running this model, and for now, we can just make a dummy variable. Oh, I guess I didn't import something correctly. Yeah, I forgot to run the first cell. So we can just make a dummy variable like a example tensor. And Torch actually has some useful functions where we can make a tensor entirely of zeros, because I don't want to write out 768 or however many numbers it is to make up the input. So we search up documentation, we get this. And instead of giving it an array of values, you can just give it the size of the tensor you want. So we want to make a tensor that is 28 by 28. And then we actually instantiate our model. So we can do model equals MLP, and then we can print model of example input. And this syntax just calls the forward function. That's what this does. We don't have to call, and we don't have to do dot forward explicitly. Kind of just does it for us. So now you can see here, we get an array of 10 values as the output. So right now, these are kind of just randomly initialized. The values in those matrices are kind of gibberish. So we need to get into how we can actually get it to predict outputs based on inputs. So that's what training is for. So we use a process called a gradient descent. What we need to do is we have a bunch of examples, right? We have labeled images that correspond to certain numbers. So we know already what the number that corresponds to that image is. What we can do is we pass that image through our neural network and we get gibberish output, right? Because these two matrices are just random values for now. And we can come up with a function that tells us how bad that output is. So one of those functions is called mean squared error. This isn't actually what we use for this data set, but it is something you'd use when you're training like a regression model, right? But just to get the intuition of what this cost function does, mean squared error is a pretty simple function. All it does is it loops through our outputs. So y hat over here means the true output, and yi represents the output from the model, right? So we subtract them and we square the number, and then we add up that value for all of the examples. And we get a final number after like running the model on like say 100 images that tells us how bad the model is or how far the model's output is from the true output. And after that, we can compute what's called a gradient. So those of you who've taken or currently taking Calc 3 might know what a gradient is. So a gradient basically tells us if we nudge this certain value in a function, how much is that going to affect the output of the function, right? So what we want here is the gradient of a weight value with respect to, or the gradient of the loss with respect to the weight value. So the loss is, in this case, mean squared error. We want a number that tells us if we change any certain weight value by a certain amount, by 1, how much is that going to change the loss, right? So we're not going to really get into how to calculate the gradient. It is in a process called backpropagation, but that's kind of out of scope for this presentation. All we need to know is that there's a really clever way that gives us this magical number, and we can use it in a step called gradient descent. So this is all gradient descent is. So first I'm going to explain what each of these variables are, and then I'm going to explain why this works. So these are weight values, right? We saw them before. That value is this value right here. It's what we multiply the input by. And then alpha, it's just an arbitrary constant, right? It's just some really small number because if we make training steps that are too large, the values are just gonna oscillate around and it's just never gonna converge. And this is our magical gradient right here. So what we're saying here is we know how much the loss is going to change if we change a weight value, and we know we want to decrease the loss, right? We want the output of the model to be closer to the true output. So what we can do is we can decrease the weight of like any certain weight, like we can decrease the value of a certain weight by a really small amount. And that should, in theory, decrease the total loss. And if we do that for every single weight value, that should overall have a benefit in that the loss of the model is lower. So that's just what we're doing here. We take our magical value, right? We multiply it by this small number, and this small number is basically what we're expecting the loss to change by. And then we subtract that from the weight value, and then we make that the new weight value. So this isn't an equality. This isn't an equation. This is an assignment. So we're saying the new weight value needs to be set to the old weight value minus this term. So let's see how that actually works in practice. So before we do any of these, we need to decide what alpha is, right? So we're going to say alpha, or it's also called learning rate, is equal to 0.0001. Just a really small number so that we don't change the weight values too much, because that would just cause the outputs to become even more gibberish. So let's define that, and let's actually, this is a good time to load the data set. So loading data sets in Torch is really nice. We can use a module called Torch Vision. And this part is kind of just copying and pasting code. But actually, here's what I'll do. This is the final notebook that we need to have. I'm going to put a link for it on the Discord. In the workshops channel. And you guys can copy paste this entire boilerplate from here to your notebook. Okay, so another value that we need to decide is the batch size. So let's see, this gradient descent step, we kind of only, or actually getting the gradient step. We kind of didn't really talk about which examples we use for this. So when we're running the loss function, a naive approach would be you run it on the entire data set, right? So you take every single pair of inputs and outputs and you compute the loss on everything, you sum them up and you get the gradients on that loss value. But that's like both kind of inefficient, especially on bigger data sets. And it's also just doesn't yield good outputs. It makes it too uniform. You want your training to be somewhat random so that it stumbles upon, you have a higher likelihood of it stumbling upon a good like set of weights, right? So what you do is you split up your data set into batches. So we need to decide what a good batch size is. Usually this just comes down to how much computational power you have. And I found out a while ago on Google Colab for this data set that a batch size of 1024 is good enough. There's also is CUDA over here, and that's what we talked about before with moving stuff in and out of memory. We can just ignore that for now. So once we run that, it's just going to download the data sets and it's going to put them into train loader and test loader. These are really nice. They're like Python iterators, so you can use them in a loop. And what you can basically do is over here, I got the first training example, and it gave us a tensor that is of size 1024 by 1 by 28 by 28. And then it also has a list of y values, the outputs. So what is it saying? There's no reason for this one dimension to really exist, but it does. We're going to get rid of it later. This is the batch size. So this is 1024 images in this batch, and each image is 28 by 28. Now we can actually try using it in training. So this is like kind of the most important part of the code. This is where we actually modify the weight values and we get a good model. So let's create our model. And let's also create an optimizer. Optimizer is just a thing in PyTorch that does this. This is called gradient descent. There are more advanced optimizers that kind of work better, but at some point it still all just boils down to this. It just makes slight modifications on top of this. So our optimizer can be torch.optim.atom. And this is where we provided the learning rate. And also what this does is it basically gives us a list of every single weight value or a list of references to every single weight value so that the optimizer can mess around with them. And now we can just loop through the train loader. So for x, y, or actually, yeah, for x, y hat in train loader, we call the model on the output, right? So y equals model of x. And then we can compute the loss. So in this case, loss equals so before we talked about mean squared error as an objective function. That's not really a good objective function for classifying between a bunch of classes. So instead we use what's called negative log likelihood. We can go into this more if we have time with you. Question?
What is Atom?
Atom is the name of the optimizer that we're using. So you can read more about it here. So remember how our simple gradient descent step is just this? Atom does a whole lot of other stuff, but at the end, it also just updates the new parameter based on the old parameter and some modifications to the gradient. This is the gradient right here. So it's just a more complicated gradient descent, and it just works better, which is why we're using it. So for negative log likelihood, we need an output and we need a target, which is the intended output. So in this case, output is y and the intended output is y hat. So with that, we have our loss, and then we can do loss dot backward. So this is the cool thing about PyTorch. Given like any computation, like any output, you can just call one function and that computes the gradient of every single value involved in that computation with respect to loss in this case. And now we can just call the optimizer. And actually, there's one step we missed here. So before we do the backward step, we actually need to zero out the gradients. So every time we run this step, it updates the gradient values. And if we keep running that again and again, it's just going to add to the previous gradients, and that's not really something we want. We want to zero out the gradients so that we aren't making redundant optimization steps. And there's a really easy to use function to do that as well. So we zero out all the gradients, we compute the loss, then we compute the gradients again, and then we tell the optimizer to perform this update step. And that should be the entire training. So let's try running this and seeing what happens. Oh, we got an error. So it says these two can't be multiplied together. Don't really know what it's talking about here. So let's try printing out the shapes. So we can see here that the size of X is 1024 by 1 by 1 by 1 by 28 by 28. This is the value that we passed in, but thing about the linear layer is that it just wants a list of vectors, right? It just wants X by N, where X is batch size and N is the size of the vector. So we need to flatten X before we can continue using it. So the way we do that is, actually, let's go back to the tensor operations notebook for reference. So we can use the dot view function to reshape a matrix. So what we can do here is say X equals X dot view. And if you remember, we can specify -1 if we want that dimension to be inferred. So that's what we're going to do for the batch size, so that we can use any batch size and this would still work. And we know the second dimension needs to be equal to 20 by 28. So now if we do this, the training loop should work fine. Yep, now it's actually running, and right now we don't really know what's happening. So let's put some print statements here. Let's try to print out the total loss after a bunch of training. So what we can do here is total loss plus or equals loss.item. Loss.item, what it does is it converts like the PyTorch attached value with all the baggage that PyTorch comes with to just a Python like float. And we add 1 to steps. And at the end of this, we can just print out the average loss. So we can see after, oh wait, that doesn't look right. This is too low of a number. I forgot an activation function. So when I said before that you're not supposed to have an activation function for Y, I lied. We do actually need an activation function, and the function we use is called softmax. So softmax is pretty different from reloop. Actually, I can actually pull up an equation of softmax. Who here knows like what like distributions are? Who's taken stat? Okay, that's not too many people. So for the people that know stat, we want the output of a neural network where we're classifying between different categories to be a multinomial distribution. So basically, we want to be able to sample. We want each value of that output to tell us how likely it is that it is any certain number, right? An example is, this is from some random paper about classifying MRI imagery, right? And they're trying to classify between different conditions. So this number needs to tell us how likely it is that it is this certain condition. In the case of our data set, in terms of MNIST, each one of those indices needs to tell us how likely it is that it's that number. So at index 0, the value of the model should be how likely this number is a zero, for example. So this is the actual like equation for the softmax function. And what it does basically is you can have the input, the domain of the input can be anything. All that matters is that the output of the softmax, if you add everything up, it should add up to 1. So we can do that right here. We can use f dot log softmax. So we're not using softmax directly. We want just the log probabilities because those are easier to work with for, or that's what we specifically need for the negative log likelihood loss function. And we say start dimension equals 1. So we know the 0th dimension is the batch dimension. We don't want to be applying softmax across that dimension. We only want to apply softmax per example. So that's what this means. Like when I said the output of softmax, everything needs to add up to 1. We want everything to add up to 1 for a certain example, not for all examples combined, if that makes sense. So once we do that, if we reinstantiate the model and run the training step again, oh, now we have an error. That is not a, oh, my bad. This means the same thing as I explained last time. So we run it once and we see that this is our loss, and that's just saying, so that is the negative log likelihood that the output of the model is the same as the intended output of the model. And actually, if we get probability out of that, kind of to try to interpret what that number means. So you have value equals this, it should be equal to negative b. So there's like what it's saying right now there is that there's a 15% chance that this model has the correct output. That's kind of low. So what we can do is we can literally just run it again, and we're gonna get a better output. And this is how you train neural networks. You do it iteratively. You basically iterate over the entire data set multiple times until you get an output that you find acceptable. So you can see here that this number is a little lower now. So now it's saying there's around a 33% chance that it matches up. And we can run that again. And you can basically do this over and over again until you get to a state where you like the model, like you like how close its output is to the intended output. And again, so any questions so far? This is kind of it for how to train a model. And if we have time, we can actually go into, yep, question.
Yeah, I need like those not working good.
What is the error you're getting?
It's the same error you had earlier where you couldn't multiply the two matrices because they had different dimensions.
Yeah, so did you try flattening it? That's what I did here, but you can also just do dot view -120. You can try cross-referencing with the link that I posted on the Discord. So after running it a few more times, we're getting this loss. Let's see. Now it's saying there's around a 58% chance that this model is accurate. Any other questions on how training neural networks works? So, yep.
Well, now that we have like this basic type of neural network, how, like, is there a way to, like, in PyTorch to make it like inference?
Recurrent neural network. So that is kind of out of the scope for um, this presentation, but PyTorch does have a really easy way to train recurrent neural networks. So if you search it up, recurrent neural networks aren't really a good method to use for, like, say, MNIST. They're more useful for a time series data set. So where you say you have a list of events that occur at like fixed intervals, or like you have a video, for example, right? An RNN might be a good use case there. And you can make an RNN by just doing this. So you don't even have to set up like the NN dot module or anything like that. But yeah. So any confusion about like the equation specifically, or what these numbers or letters mean? Cool. Okay, so now we can actually clean up this code a bit and make it a little bit more usable. So we know we want to run this over multiple times over a data set. That's called an epoch. So every epoch, we iterate through the data set 10 times. But say we want to do 15 epochs in total. Just completely arbitrary number, works generally well in most cases. So we can just start a loop here for, we call this epochs. For and range. We just paste this code here. And at the end of each of the epochs, we can just print out the loss again. I didn't like that. And after this, we can also try running the model on some examples from the data set and seeing what that does. That wasn't a very useful source. We can see as we keep running this model, it gets better and better. So let's find a training example to actually run this model on. So we have our data set over here. Let's run it on something from the testing data set, right? Stop that from running. Let's try doing this. So if you look at the size, we can see this is just one MNIST image. And let's actually try to plot this. We can use a library called matplotlib for that. So they have an example here where they plot an image. So let's see what they first converted it to an NumPy array. So let's try doing that. So that works. And then let's call the plot function on it. I did not like that. Maybe let's try removing the first dimension. So there we go. This first example in the test set is an image of a 7. So if we try running the model on it, let's see what happens. So we get this. Instead of just looking through this, we can call a function called argmax. And let's just torch argmax. And we can see the output is a 7. I actually was not sure if that was going to work or not. Let's try some other example. So that's supposed to be a 6, but it's not super, might not be super obvious, but the model predicts that correctly as well. So instead of kind of just looping through the test data set manually, we can also just do this in an actual Python loop and calculate what's called the test accuracy. So this typically you'd also do this at the end of each epoch. So before the start of an epoch, we do model.train. What this is saying is we want the gradients to be computed. But when we're testing the model, we don't really care about the gradients being computed. So we can say model.eval. And these are both functions in PyTorch. So all that model.eval does is it basically says, all right, you don't need to keep track of the gradients. And if anyone calls backwards, throw an error because they're not supposed to be doing that. So now we can do the same thing as this, but instead of going through the train loader, we can go through the test loader. And we get y equals model of x. And we don't need any of this anymore. We can still compute the loss on the training set, but that's not really as useful as, say, computing the accuracy on the training set. So there is a function that helps us compute accuracy. Never mind, it's not in PyTorch. There's another library which helps us compute accuracy, and that is called scikit-learn. And over here, you have a question?
What does model.train and model.eval do again?
Yeah, so model.train tells the model that it needs to keep track of gradients, and model.eval says it does not need to keep track of gradients. There are also a few other things that model.train and eval does. Like there's a method called dropout. And all dropout does is, this is not a good explanation of it. So say we have a standard neural network like here. All dropout does is it just randomly kills some neurons. So it just randomly sets the output of some neurons to 0. And that forces the model to take different paths of information, essentially, if that makes sense, to get to the same output. And this is what's known as a regularization technique, and it causes the model to not overfit. So actually a brief explanation of overfitting and underfitting as well. So this is underfitting. It's where the model doesn't really represent the data very well. And this is a good fit. It's where the model mostly represents the data. And overfitting is when it is too specific to a certain set of data. So it's if you say added another, if you tried another data set where over here you have the circle instead of the cross, this model would predict it incorrectly because it's basically tuned to a specific data set too much. So dropout is useful for reducing this from happening. So when we do model.train and model.eval, it also does things like turn dropout on and off. Because dropout isn't something we want while we're actually running the model, we only want it for training purposes. Yep.
Yeah, so if we're having the model keep track of its own gradients, do we need the optimizer then?
Optimizer doesn't like compute the gradients. Optimizer applies the gradients back to the weights. So gradients like the partial loss over partial weight value is stored alongside the weight value, and all the gradient does is or all the optimizer does is it contains this code. So it takes the gradient, messes with it, and then applies it to the weight. Some optimizers have like values of their own, like they have their own state. Like the atom optimizer, it not only has this gradient, but it computes a bunch of other values that are for each weight value that it uses to converge quicker. So we can do, let's see. And I think I might need to convert these to NumPy, possibly. So I'll just do. And the output needs to actually be argmaxed again. So and for now, let's just comment out this code. Just see if this code works. Okay, so it's saying if there's a tensor that has a gradient attached to it, we can't just call NumPy on it directly. We need to detach it first. So that's just a PyTorch thing that we need to be aware of. And it says metrics isn't defined. Worked correctly. All right, cool. And looks like that there are no errors there anymore. So let's print out the total accuracy at the end of this. So we can see that we're getting around a 92% accuracy on the testing set, which is not bad after how long we trained for. So that's it for this workshop. So if you have any questions, you can keep them coming, and yeah. Yep.
Go down a little bit.
Oh, yeah. Which part do you want to look at? Over here. All right.
Will it be all on Discord or?
Yeah, I'm gonna post all the notebooks on Discord.